Okay, this lesson is for section 3.4. We're going to be doing a bunch of graphing here, and the graphing that's going to take place is based off of your memorized graphs of your 6 mother functions. So what I'm going to do is introduce you now to your 7th mother function, the greatest integer function. Okay, so there was a picture of it, but let's talk about it more in depth. Okay, so now the greatest integer function, I think, is kind of a confusing title for it, because what it does is for any real number, so your domain here is all real numbers, you can input something and it's going to output, your output will be the greatest number, the largest integer I should say, that's less than or equal to x. So let's say I put in 2.56, okay? The output of this is supposed to be the largest integer that is less than this number or equal to it. So the largest integer that's less than this number or equal to it is actually the number 2, which I think intuitively kind of makes no sense when it says greatest, right? Because this number is actually not bigger than this number here. It's going to truncate that value and give you just 2. Now, it gets confusing even more so when you see a negative value plugged in, like negative 1.4, okay? Most of you guys, knowing what we just did here, would say, oh, then my answer should be negative 1, right? The output here, y is going to equal negative 1. Oh, I should have used y equals over here too. But that's actually incorrect, okay? So to help explain this, I actually like the title floor instead, okay? I'm going to take a normal number line, you know, one of these guys, and I'm going to flip it. I'm going to invert this so that now it becomes vertical. Alright, so bear with me here. I got to make the number line first. Okay, now I'm going to oil this bad boy up, okay? He's going to get real slippery now. So I throw some grease on him, and now I try to input a number like 2.56. So I want to graph 2.56. Well, I put it on there, but uh-oh, it's all slippery, it's oily. He falls down to 2. This is why we get y equals 2. Well, it's not really why we get it, but it helps to visualize why we're getting y equals 2 when we do a greatest integer function. Now, if I plug in negative 1.4 and I try to graph that, plot that point here, again, it's slippery, it's going to fall, and boom, I land at negative 2, okay? So it's really tricky to do a negative value if you don't visualize it first. This will definitely help you to just visualize this. It's also called your step function because if you look at your graph here, you're looking like you're taking steps, right? So again, visually you can see the same thing here going on. Let's say I took that same number, 2.56, right? X is 2.56. I go up to it and I have a y output of 2, all the way up until I get to 3. So let's any number that I plug in for x in between 2 and 3 ends up being an output of 2. As soon as I get to 3 though, now I have an open circle. This function jumps up to the next step, which would be 3. Alright? I hope that makes sense, because now next we're going to talk about transformations. Alright, so here is the basic graph for y equals the absolute value of x. Alright, this is your mother function, y equals absolute value of x, which you should have memorized again, but also I'm bringing this up because last year you would have studied this a lot. You would have talked about transformations a bunch, and it's kind of one of the easier graphs to see all the movement that occurs. Last year you would have used words like stretch and shrink. This year we're going to use vertical compression and vertical stretch. So it's a little bit slightly different terminology, but it still means the same thing. So when you think of compressing something, you know, I don't know, this is silly, especially since this person is not really a good stick figure. But if I were to compress this guy, meaning I'm going to shrink the ceiling and the floor and push up on him both ways, well, eventually he's going to get fatter, right? He gets wider and to try to accommodate and fit into that space. So compressing him means that your values get smaller and your graph visually gets much wider, okay? So hopefully this makes sense when I start transforming this. Alright, so I'm going to take this function, I'm going to move it over, and I'm going to put my vertex now at, let's say, 3, negative 2. Okay? So now I'm using the graph of this function. So if I were to find the equation of this, it actually ends up being, oh, sorry, let me write the vertex. The new vertex is at 3, negative 2. Okay? This is actually what represents this function. This is the equation of this graph here. Now, you'll notice that the inside of that number was actually the opposite of what your x-coordinate was for your vertex. And that's because numbers on the inside like this actually shift it horizontally, but to the opposite direction. So we started at the point 0, 0, we moved it 3 units right, and then we moved it 3 units down. Okay, that is what your number on the outside does. So this is a movement vertically, up or down. In this case, it keeps the same sign. So you would think it would change it and go down, and it certainly does. It shifted your graph here down 2 units. This number on the inside, though, however, it shifts it left or right, and it's going to go the opposite direction of what you think it would. So even though it's a -3, we go to the right 3. Okay? All right, so that's a basic understanding. Now, if we're talking about shifts that are occurring, as far as vertically stretched and shrunk, then it gets a little bit trickier, but let's see if we can try to explain that. So I'm going to erase some of this right now. Okay, so I'm going to start with doing a stretch. So a stretch means that I'm going to put a value on the outside. This is going to stretch it by a factor of 2. When you're graphing an absolute value 2, I don't know if anybody's ever talked to you about slope, because technically it's not really, you shouldn't really call it the slope of the line, but I'm going to quickly graph this by going up 2 and to the right 1, and then left 2 into the right 1, or sorry, up 2 into the left 1. And that would be the graph of the equation y equals the absolute value, or 2 times the absolute value of x minus 3 minus 2. So what you're seeing here now is your guy getting, it's the normal guy, now he's getting stretched out, right? He gets skinnier as he gets stretched. So think of like Stretch Armstrong. If you like stretch him out, he gets a lot skinnier. And that's why you're seeing the shape of your graph much skinnier than your normal absolute value graph. So if this number here on the outside is greater than, its absolute value is greater than 1, then you're going to get a stretch. If the absolute value is less than 1, so let's say it is now going to be y equals 1/2 times the absolute value of x minus 3 minus 2. This time, this is a compression. And if I graph here, so I go up 1 to the right 2, now all of my values have shrunk. And that's the word that we use in 90s, is we call it a shrink. So all of these values, if you look, have been shrunk down, these y coordinates. So this is actually a change in your y value. Basically, you have changes in your y's, okay, and a change in your x value here, horizontal change. And that's basically the gist of it. Oh, forgot one more. If I put a negative on the outside of this, all that does is reflect it over the x-axis, so it would open down. So that green function here now just would open down. Alright, so let's get back to your note sheet. So just to review, again, I have all the translations here written out for you. So a flip over the x-axis is a reflection, and you're going to see that with a negative on the outside. A shift to, well, let's go to the next one. A flip over the y-axis has the number appearing on the inside. I didn't do that with the absolute value graph, but we'll do that coming up real quick. Now, a shift left occurs in the horizontal or your x direction. So left to right is determined by a number that is on the inside of your parentheses. Okay, so the inside next to your x value. When a number is going to shift the graph up or down, it's going to appear on the outside, and it goes the same direction that you think it would. Okay, so let's go through and try to graph these quickly. So our idea here is to graph these very, very quickly now. Now, first we want to recognize this as the mother function, y equals x cubed, but just been translated down 2 units, right? So think about your graph of your mother function, y equals x cubed. Hopefully you have the points memorized here. 2, 8 would be my other point here, and -2, -8 would be my other point down here. And that's what my mother function would look like. Well, now I'm just translating this down 2 units. So I can think of this a couple different, whoops, got that one wrong. I can think of this a couple different ways. You can algebraically find the coordinate, right? I'm not graphing that very closely. It should be hitting through here. You can find that coordinate because it's going to only affect the y value. So you have your points memorized, right? 0, 0, 1, 1, -1, -1. You have those points already memorized. Now all you're going to do is subtract 2 from each of the values, right, in your y. So that's why we ended up at 0, -2. We ended up at 1, -1, and we ended up at -1, -3. So you can see that reflected here in each of those coordinates. Alright? Now, the second one here is also the mother function y equals x cubed. This time, we have been shifted to the right. So this number is on the inside with the x in parentheses, so we're going to shift it to the opposite direction than we think, which is going to make it move to the right. So you can do this before you even, since you have your points memorized, right? List your points, and then shift these all to the right by adding 3 to the x column. So now you have a point at 3, 0. You have a point at 2, negative 1. Or sorry, 4, 1. What am I saying? 4, 1. And 2, negative 1. Oh, I was right. I don't know why I think I'm wrong. And then you can also do that for your point 2, 8 as well. So this should end up at 5, 8, somewhere up here. And also down here, if your normal graph would have been negative 2, 8, then you're going to shift this to the right by adding 3, and you're ending up at 1, negative 8. Oops, possibly. Alright, so this is what the graph here would look like. And again, we're doing this very quickly, right? We don't need to write a table and make our x, y, and because we already know a lot of these points, and we can do these in our head as well. I'm just showing you the work. Alright, now, greatest integer function. This one has been moved to the left 1 and up 4. I'm going to let you guys do this just to save some time here, because we still have a whole lot more to do in this graph. Along with this one, this is going to be your mother function y equals 1 over x, so it's going to be translated 2 and up 3. So, you know, take your point 1, 1, and negative 1, negative 1, and translate those points only, and then you can just draw your, oh, it's also got a horizontal asymptote at x equals 2, right? I know you guys covered that before, but so it can't cross this axis, but basically you're going to end up with these 2 points here, and you can just draw in the branches. Okay? Alright, now let's go to this guy. Alright, so this is the square root function. Y equals the square root of x. We know that this is going to look like this. Now, I want to do a few different translations here, but I want to do them and make sure that they're in the correct order. So when you do your translations, you first want to do, just like order of operations, you would want to multiply your values by negative 1. In other words, you want to flip before you do any horizontal translations or this last vertical translation. So I'm going to flip this over the x-axis. So now my graph should look like this. Okay? This here shifts my graph 2 units to the left. So I know that my point should shift from 0, 0, left 2 units, and then down 1 unit. So now this is the starting point for that square root function here. And I know it's going to open down, so the next point should be down this direction. And I can go down 2 and to the right 1, 2, 3, 4. And that would be my graph. Okay, so very quickly I just graphed that. Now, the only problem with doing these translations is when you get to a problem like this. Now, if you just looked at this value here and said, oh, it's going to go opposite, so it's going to go left 2, you would actually be wrong, because we see the opposite of x. So this is actually a reflection in x, or sorry, over the y-axis first, but what I want to do is have you guys rewrite this. So even though it's going to be a square root function, I want to have you rewrite this and factor out that negative so that you have a positive x and then minus 2 here, so that you can actually see the translation that's going to occur. So first things first, this would be our normal y equals root x. This time now we're reflecting it over the y-axis, so it's going to flip and go this direction. Okay. Now the starting point is going to be translated 2 units to the right and down 1. So we're going 2 units to the right and down 1. So this is my starting point, and I know it's opening in this direction like that. So I have a point here, a point up 2 and to the left 4, and this would be my square root function here. Alright, I don't have numbers on, but this next one is a circle, semicircle, right? Semicircle is dictated, hopefully, you know, I talked about this in class, but this number here tells you what the radius of that semicircle is, and it doesn't actually tell you here if it's translated up or left or right. It just tells you, determines the radius. This number on the outside here is shifting my point 0, 0 up 1, 2, 3 units. So that would be like in my semicircle function, which looks like this, right? That's kind of like your center of a circle if it were to finish off the whole thing. Well, we're now translating that up 1, 2, 3 units, and now we're increasing the radius to 2. So it would look like that, but it's translated up. So now my graph looks like this. Okay? Alright, next up. This one I think is kind of confusing. This is y equals x squared. Now, if you were to recognize this is a different function, I'm not sure where you would go with it, but you could also use a table of values. But okay, so it's y equals x squared. Again, this has a negative value in front of the x, so I'm going to factor that out, and I'm going to call that negative, or opposite of x minus 1 squared. Okay? This is a reflection over the y-axis. So here's your normal graph of y equals x squared. Well, if you reflect it over the y-axis, you get the exact same thing. Okay? It literally doesn't move at all. We always want to make sure we're going in order of operations. We have to do this reflection before we move it right 1. So this does move the graph right 1. So now I have my vertex there at 1, 0. And I have points at 2, 4. Let's see, or sorry, 3, 4 that was. And then here and up here. Okay, so that's the graph of this guy. Now let's say you did it in the wrong order. This is one where it's going to be really obvious that you did it in the wrong order. Let's say you were like, oh, I'm going to translate it 1 to the right. Well, then you would end up with the graph here, and then if you flipped it, it would actually move over to this side, right? If you flipped it and reflected over the y-axis. So that's why it's very important to do order of operations here. You must, do your flips before you move it horizontally or vertically. All right, next. I'll let you guys do these next few because this is, I think, pretty basic. Here, this is just going to move every single point 2 to the right. So all I really need you to do is take each of these points, move them 2 to the right, and then graph your new function like so. Okay? Alright. So in this one here, obviously there are 2 different translations. Alright, now finding the range for the function. If you know what this looks like, now it becomes really, really easy for you to find the range. So I would actually sketch this first and then find the range. These would normally be functions that it would be probably pretty difficult to find the range for because, you'd solve for y, or, this would be a radical equation. You'd have to solve for the x and then look at your restrictions. Same with this one. I don't know if you remember from before, but that was a really tough problem that we did in the first day of notes, except for it was, I believe, negative 3 plus root, I think 4 minus x squared. So that one was a tough problem, and a lot of you guys had a hard time understanding why the range turned out the way it did when we solved for the restrictions on the y when we solve for x. So algebraically that's tough to do, but if you do a sketch it's pretty easy. So this graph is going to be reflected over the y-axis, or x-axis, sorry, so it's going to look like that, and it's going to be shifted left 2 and down 1. So left 2, down 1, and opens like this. Well, you see your high point here is at y is equal to negative 1, right? So y is going to be less than or equal to negative 1. That would be your range. So if you write that in interval notation, then we have, open bracket, negative infinity up to negative 1, close bracket. Alright, now, number 2, again, really easy to do once we know what the graph looks like. This is a semicircle, and this semicircle has a radius of 2, and it's been translated up 3 units. Oh, did we just do that one? I think we did on the first page. Okay, so I already have the graph of this. So if we were looking at the range, this is super easy now to find. We have a low point at y equals 3, and our high point at y equals 5. So our range here is just in between 3 and 5 inclusive, right? So it's going to be closed brackets there. So that's very, very easy. No algebra, because we know what the graph looks like. Okay. Sorry, I'm taking so long. I know this is pretty long. Thanks for sticking in there. Okay, for the point 2, negative 4, it lies on the graph of f. So we're going to take 2, negative 4, and we're going to do translations based off of this. So we don't actually have anything to plug this into. We're just going to look at these and look at our translations and what's going to occur. So we have changes in our x, right, which is going to come from that number on the inside here. And we have 2 changes to our y values. The first y value transformation, though, has to be this. It's going to be a reflection over the x-axis and a factor of 2 that it's stretching it by. So if we reflect it over the x-axis, then this point now becomes positive 4, right? And if we multiply it now by 2, then it becomes 8. Shortcut, obviously, just multiply by negative 2, and you get positive 8. So now we have the point 2, 8. So that's after our first transformation. Now let's do our second transformation. Let's do this guy. We're going to move the x-coordinate 1 unit to the right, which means we're now going to add 1 to the x-coordinate to get the point 3, 8. Okay, so far so good, hopefully. Last transformation. This is going to affect, again, in the vertical direction. It's going to shift it down 2 units, so that means I'm subtracting 2 from that 8 to get the point 3, 6. So you'll be doing this in your homework and maybe possibly on test or quizzes, so make sure you understand what that's doing here. Alright, last but not least, I want to discuss even and odd functions again, just to hammer this home with you. When something is symmetric about the y-axis, then this must be true for every point. When you input f of negative x, you get it's the same y output for f of x. So this point here, f of 2 is equivalent to f of negative 2. They are at the same exact y output. On the other hand, when something is odd, it's symmetric about the origin, then you can plug in f of negative x equal to the opposite of f of x. So in other words, let's see the point 2, 8 here. This is our cubic function. 2, 8 and negative 2, 8, which should be about right there. Negative 2, negative 8. Why do I keep saying that's positive? These are, if you can see, you have your opposite x value and your opposite y value. So if you plug in that function, the opposite of x, so in other words negative 2, then you end up with the opposite of your y value. Okay? Now the last question here, which of the mother functions are even, odd, or neither? Well, for an even function, we have y equals x squared, of course. We also have the function y equals 1 plus the square root of 1 minus x squared. We have, what else? I'm just trying to graphically think of our main functions. Actually, let me see if I can pull that up really quick. Where is it? There we go. Okay, so symmetric about the y-axis would be an even function. So we have an even function here, an even function here, an even function here, and that's about all. The odd function is going to be these two guys right here. Okay, I believe that about does it for this lesson. Thank you so much for listening, folks. Oh, and then the neither, sorry. This would fall into the neither. He's so sad, not symmetric. Okay, bye-bye.